It's a great honor to have Professor Severson today here to give us a seminar talk. And please allow me first to give a brief introduction to Professor Severson. So he received his PhD from University of Minnesota in 2015. In 2017, he joined the faculty of the Electrical and Computer Engineering Department at the University of Wisconsin-Madison. He currently holds the University of Wisconsin College of Engineers named Granger Assistant Professorship, and is also Associate Director of the Wisconsin Electric Machines and Power Electronics Consortium, or better known as WEMPEC. He received the 2020 NSF Career Award for electric machines that can be actuated across all 6 degrees of freedom. His research interests include design and control of electric machines and power electronics, with focus areas in Bearingless motors, magnetic bearings, flywheel energy storage, and off-highway vehicle and hydraulic system electrification. He is also currently a guest editor of a special issue of the IEEE Transaction on Industrial Applications on Magnetically Levitated Motor Systems. So with that, Eric, please take the floor. Thank you very much.
Thank you, Bingman. Thank you very much. It's a pleasure to be here with you all, virtually at least, and I hope we get a chance to meet in person sometime soon, perhaps at a conference. So yeah, I'm Eric Severson. As Bingman said, I'm an assistant professor here at the University of Wisconsin-Madison, and the title of my talk is kind of playfully "Use the Force for Good." And force means magnetic forces, magnetic levitation forces. And so we'll talk about that, but before we get into that, let me just make sure this is working here. Just a second. Oh, okay, now it's responding. Okay, great. Before we get into the core of the talk, I want to give a little bit of a background on where I'm coming to you from and our research. And so I'm, as Bingman said, I'm an associate director of the Wisconsin Electric Machines and Power Electronics Consortium, or WEMPEC, as we like to call ourselves. And we're an industrial consortium, or a consortium of 4 faculty here at the university and about 75 industrial sponsors. We were founded back in 1981 by famous professors Tom Lippo and Don Novotny to really try to bring together current thinking on electric machines, power electronics, and controls, and to help industry adapt knowledge on this to make better electric motor systems. And so our research spans all 3 of these topics, and we focus on the intersection of the 3 topics. So the whole electric motor system. We currently have 4 professors here at UW who are focusing in this area. We're hiring at least 1 more this year and perhaps more in future years. And we've got 3 full-time staff, over 50 graduate students, and we have had a pretty big footprint. We've over 160 PhDs that have graduated, over 425 MS students, and these numbers are a few years old. I think they're quite a bit higher now. Yeah, and this is just a little glimpse of what our labs look like. We've got capabilities to make simple prototypes of electric machines. So here's a couple of my students in the basement of Engineering Hall. They're installing a stator winding of a motor. Here's an image of our laser cutter cutting out laminations for a linear machine. And we also have great testing capabilities. So we're able to, I think our highest power test dyne is 170 kilowatts and can go up to, I want to say 15,000 RPM. My group is working on higher speed test dynes, slightly lower power. So we're working on building up to be able to test a motor at 160,000 RPM right now, and instructional facilities. And my group, so I'm a part of WEMPEC, and my niche, what we try to carve out for ourselves, is really the intersection of high torque or high speed motors, magnetic levitation, and controls. And so this talk is focused on the magnetic levitation and high-speed motors aspects of our work. But we also work on machines that aren't levitated at all, but are instead really trying to push the boundary of achievable torque density and form factor. So here's a few pictures of what my group kind of looks like. We like to build prototypes. That's kind of a thing about WEMPEC. Everybody here likes to build things and see their theory brought to real life. We've been working on an electrostatic project recently. One of the other WEMPEC faculty members is an electrostatics expert, so he makes motors that operate not with magnetic fields, but with electric fields instead. And I've been working with him on a electrostatically levitated flywheel project. And our work is funded from a variety of partners. We've got NSF funding, Department of Energy, Army Research Labs. A few companies have been supporting our work recently. And yeah, and so that's kind of an overview. My favorite picture that I have of my group, you know, unfortunately, so I've been here for 4 years, and I just finally had my group really up and running when the pandemic hit. So we haven't actually all gotten together and posed for a formal group picture, but this was a couple of months before the pandemic hit that we got a picture of my group having an end of semester celebration and learning about magnetic levitation toys. So this poor guy up here is trying to teach us how this magnetic levitation toy works, and everybody is busy taking Instagram photos of a floating globe on the table. But that was a very fun day. And before I get into the talk in earnest, I wanted to showcase one other aspect of our research, which I think may be of interest to some of your initiatives at MERL. And that is our work on not magnetically levitated machines, but really high torque density machines. And we've got a series of projects supported by the Department of Energy on trying to increase the torque density of motors for off-highway vehicles. And so specifically, we're thinking about trying to electrify the implements of off-highway vehicles, you know, things like this bucket up here, or the boom actuators. And this is a hard thing to do because if you look in this space, hydraulics are in there right now, and hydraulics have this kind of insane torque density of upwards of 600 kilonewton meters per meter cubed, whereas motors, you know, commercial motors you can buy today are somewhere between 10 and 30 kilonewton meters per meters cubed, and those are pretty high torque density motors in and of themselves. And so we've been thinking about different ways of doing this. We're interested in partnering on future projects, and so if this is a discussion topic that you'd be interested in, I'd be happy to engage with you. One of the things kind of looking forward is we want to start leveraging more magnetic gear concepts and torque on multiple surfaces, which I know MERL has worked on before. One of our current success stories right now is a PhD topic for one of my students, Nishant, who was your intern this last summer. And so these are a few 3D CAD renderings of his work where he has been partnering with a hydraulics student and has created a electric machine and hydraulic pump that are all a single, so it's a single electric hydraulic machine. Surfaces of the motor are reused as surfaces of the pump, or as the hydraulics team likes to say, surfaces of the pump are reused as surfaces of the motor. And so we've built up a module here that has quite good power density when you look at it from the perspective of it being both an electric machine and a pump at the same time. All right. Now let's get on and talk about the Force. And so, of course, we have to have some Yoda memes. Be much better if I was in person and we could crack some Star Wars jokes and not just send them out into the ether. But so we'll talk about not this kind of force, of course, but the forces produced by magnetic fields. And so kind of the background of this talk in the highest level, thinking biggest picture, is that it's about electric motors and how to make electric motors more sustainable and last longer and be more reliable. And why do we care about that? Well, because electric motors have become absolutely fundamental to our modern lives. They pump the water that we use. They generate our electricity. They heat and cool our homes, our workplaces. They're all over in our electronic devices, from little fans to actuators, hard disk platters, and so on. And so perhaps it's not surprising then that motors are the single biggest consumer of electric energy and are estimated to consume around 45% of global electric energy. And so if you're interested in sustainability, electric motors have absolutely got to be part of that conversation. I mean, when you see statistics like this, you can think that, you know, even very small incremental changes of efficiency of a motor, you know, 0.5% or 1%, if is scaled out to the entire user base of motors, it has an enormous impact on our worldwide energy consumption and carbon footprint. And so this talks about motors, but really it's about motor bearings and why we want to get rid of and getting rid of motor bearings. And so just, you know, motor bearings, what are they? Well, now they're these things, right? They're these pieces that keep our shaft centered while it rotates. So we talk about them being ball bearings, journal bearings, air bearings, magnetic bearings, so on. Mechanical motor bearings are really kind of the Achilles heel of motors. So they are typically the first point of failure. They're a source of losses in electric machines, especially high-speed electric machines, and their lubricants can cause problems in the broader systems that they are used in. And so I've got a couple slides here that I just want to showcase a few examples where motor bearings are particularly painful along those three lines. So the first example is that of a turbocharger. Turbochargers, as you may be familiar, are becoming increasingly popular as a means of making internal combustion engine driven vehicles more sustainable. And so it's kind of a near-term stopgap to increase sustainability here while we work on electrifying our fleet. It's also an enabling technology for or a sustainable, perhaps a longer-term sustainable technology for vehicles that aren't immediately ready to be electrified, such as large trucks or off-highway vehicles and so on. So what can you do with a turbocharger? Well, you can compress the air intake to your combustion engine, and that allows you to downsize the engine. In fact, it's fairly well known that if you do this to a typical passenger vehicle, you can actually decrease fuel consumption by upwards of 10%. And it can be used to enable a technology called gasoline compression ignition. It's kind of like dieseling for a gasoline car. And this technology can increase fuel efficiency by upwards of 25 to 35%. So there are big sustainability implications here. These devices, they basically, you think about it as a fan spinning really, really fast. They're typically using journal bearings to do this, and they spin, like I said, really, really, really fast because they want to be really, really, really small. So every kilogram, every pound that you can take out of a car has implications both for the size of the car and also for the fuel consumption of the car. And so for this reason, turbochargers are driven upwards of 300,000 RPM, and they're exposed to high temperature because they're right in the exhaust stream of the engine, and they use that exhaust energy to compress, to spin the fan and then compress the air going into the intake. So this combination of really high speeds and high temperatures is rough on bearings. In fact, 80% of turbocharger failures are due to bearings wearing out. And the frictional losses in the bearings cause some real problems. I mean, of course, they cause efficiency reduction. That's not great. But perhaps even more troubling is that they contribute to this phenomenon called turbo lag. And turbo lag is experienced by drivers when you come up to a stop sign, you know, your vehicle is stopped and you hit the accelerator to go. It takes some time for your turbocharger to spin up and provide the compressed air intake, to provide the compressed air to your engine intake that you need to get going. And this is largely contributed due to friction in the bearings that prevents the shaft from accelerating very fast. And so it's a real noticeable thing for drivers and a problem. The last thing then is oil contamination or issues with lubricants. So if your lubricants leach out into your engine and combust, which they inevitably do, this adds emissions, creates smoke in the exhaust, and is doing things that you don't want to be doing when you are trying to increase the sustainability of vehicles. So this really touches on all three of those aspects we mentioned in the previous slide, which was reduced lifetime and friction causing problems, and then finally the issues with lubricants and the broader systems that motors are attached to. Second example I've got for you is one of my favorites. This is HVAC, heating, ventilation, and air conditioning. And in HVAC systems, of course, you want very, very efficient equipment. If you have losses in your motor, well, you know, that is a watt of heat that ends up in your building that you have to take back out if you are cooling it. So every watt counts twice. And HVAC, it represents about 17% of U.S. energy consumption. So it's a major topic area when we talk about trying to decrease our carbon footprint and our energy footprint. What I want to key you in on is very large chillers like this one here. This is a chiller that's up on top of one of our buildings here on campus. And I've got another picture where I'm standing next to it. It's taller than me, so it's a very big chiller. And it's used in the HVAC system. It chills water that is then circulated down through the building and used to cool rooms within the building. And these types of systems historically have been driven by electric motors using journal bearings that drive a centrifugal compressor. And those journal bearings, again, require lubricant, and the lubricant sort of inevitably leaches out into the refrigerant of the system and ends up coating the heat exchange pipes. And when it does that, it decreases the thermal transfer, it decreases the ability to draw heat through those heat exchangers, which is exactly what you don't want to have happen. You have a heat exchanger to exchange heat. And so this is a fairly large problem. Trane did a study on this, and they showed here on this plot that how a percent of oil in the refrigerant contributes to overall efficiency loss in the entire building. And so you can see that, well, you know, if we're sitting here at about a 4% of oil in our refrigerant, that corresponds to what, like a 7 or 8% reduction in entire building HVAC efficiency. And you know, these large systems are on the order of megawatts, right? So this is a very large amount of kilowatts just lost due to oil being in the pipes. Trane went out and surveyed their commercial installations and found that the smallest level of contamination in any of the buildings that they studied was 3%, leading to a 5% reduction in efficiency. The largest was 23%, which is like off this chart, right? So you can see that this is a major problem. And not surprisingly, the large HVAC OEMs have responded, and all of them now have a product line that uses active magnetic bearings in place of journal bearings. They call them oil-free chillers. And Daikin, Trane, all of the companies have a product line around this. Okay, so that brings us to active magnetic bearings. Well, this talk is really about two technologies. One is active magnetic bearings, which we'll define in this slide, and then the second is bearingless motors, which we'll talk about in the next slide. So active magnetic bearings, what are they? Well, an active magnetic bearing looks a lot like a motor. So here's a picture of one down here. It looks a lot like a motor, and it functions in a sense like a motor, only it does not produce torque, it produces radial forces. So this is the stator of a magnetic bearing. The shaft goes through here, and what the stator does is it creates X and Y forces on that shaft, or radial forces on that shaft. And you can see it looks like a motor in that there's laminated steel. There's coils wrapped around teeth, and not shown here, but you'd have a power electronics cabinet next to it. There's power electronics that are driving currents into it. So the advantages of using active magnetic bearings over conventional bearings are fairly clear. Your active magnetic bearing is in a sense floating your shaft. It's levitating your steel shaft. And so if your shaft is floating, well, if your shaft is floating, well, it's friction free. There's no need for any lubricant. And you have lots of sensors to do this. You know a lot about your shaft, and you can use the data from those sensors for health monitoring. You can observe things like if new vibrations develop and respond proactively. But the challenges are very significant with active magnetic bearings. And so far, they really only make sense in certain niche applications like HVAC, like very large HVAC systems, in fact, not small ones. What are the challenges? Well, these bearings are big. They have a low force density. I mean, especially compared to like a ball bearing or a journal bearing, They are big. They're difficult to integrate. There's lots of wires that have to be routed. You know, they come with a lot of sensors that have to be very precisely aligned. Everything's got to be aligned, installed just right. And finally, they can lead to broader, unexpected system behavior if the control isn't properly implemented. So kind of a classic example is cross-coupling with a motor. Your motor has got unbalanced pull to it, meaning that if the shaft of your motor is centered, there's no forces on it, but as soon as that shaft becomes eccentric, a very large magnetic force will develop and pull it to the side. And later in the talk, we're going to talk about controlling that magnetic force to make the motor behave as a magnetic bearing. But when you have magnetic bearings on here, that force is a problem. It's a destabilizing force, and it can lead to bizarre behavior of your shaft. So here's a plot of a rotor orbiting in the air gap of the machine. And with conventional bearings, you'll always have some, it's called a runout. You'll have some shaft runout. The shaft will move a little bit. With magnetic bearings, it tends to be a little bit bigger. And if your control isn't tuned right, it can be so big that you risk having to shut the system down because it could crash. Okay, so that was active magnetic bearings. The other technology we're talking about, and this is where most of the research is right now, is in bearingless motors. So a bearingless motor is an electric motor that can produce torque, because of course motors produce torque, that's the fundamental thing that they do. But in addition to producing torque, the motor can also produce either radial or axial forces. So the idea is that you're using the same steel of your motor, but now you've modified your magnetic field so that it's able to produce force as well as torque. And you can do this to make your motor behave as a bearing and replace one or more of the motor system's bearings. So you've got your motor, it now functions as if it's also a magnetic bearing. You then can eliminate one or more bearings from your system. And this has potential to solve a lot of the challenges of magnetic bearings. We're going to talk about that later in the talk. But for now, let's just focus kind of on the higher level story here. And it turns out that you can design any type of motor as a bearingless motor. All you have to do is introduce a second magnetic field into your air gap that makes these forces. And so practically speaking, that means that you can take any motor and you can add a new winding to its stator to make it function as a magnetic bearing at the same time. Okay, cool, neat trick, huh? So what can you do with this? Well, I'm going to walk you through two example use cases. In the first case, I want you to consider kind of the classical motor system that we've had ever since the advent of motors, going back 150 years. These are kind of what the first big motor systems look like. You'd have the power grid, three-phase coming into an asynchronous machine, like an induction machine. And that machine might be very large depending on the power rating, and typically is supported on journal bearings, and that requires their own infrastructure. You'll have some kind of pump system off to the side. It's kind of dirty, it can be leaking oil. The motor has a shaft that goes to a gearbox, which steps the shaft speed up to a high-speed compressor. The compressor then is used to drive a broader system. And the point of control for this kind of system, if you want different amounts of power coming out, is that you'll have throttles in the fluid that the compressor is compressing. You'll have throttles in the path of that fluid. And according to the Department of Energy, in these kind of systems, upwards of 80% of the power is dissipated in those throttles. So we have we're drawing all this power from the grid, and then we're just dumping upwards of 80% of it in throttles. And the reason is that you have to size this motor in this system for the maximum power that you'd ever want to draw from it. And then you throttle it down for nominal cases so that you can open the throttle up and have more power when you need it. Okay, so this is a classical motor system. Magnetic bearings. Well, first off, one of the things you can do to improve this classical motor system is that you can, instead of directly driving your motor from the power grid, you can introduce a variable speed motor drive. And this is done. This certainly is a valid solution. The problem with it is that variable speed motor drive introduces electromagnetic interference that tends to cause currents to flow through your bearings and wear them out. There's numerous studies on the lifetime reductions of these bearings due to motor drives, and it can be upwards of a 50% reduction in lifetime when you add a motor drive. So the magnetic bearing system kind of leapfrogs this issue. You can put your motor drive on here because your magnetic bearings are levitating your shaft. There's no place for those bearing currents to flow. So in this case, we've got a motor. We're going to right away make it a high-speed motor because our compressors like to be high-speed. Motor is high-speed, it becomes smaller. Compressor is higher speed than it used to be, it becomes smaller. Your shaft is levitated by these magnetic bearings we talked about. And so you add electronics for the variable speed motor drive, you add electronics for the magnetic bearing controller. Now and then you better throw in a battery backup system because you wouldn't want your shaft to crash down at 30,000 RPM if the power grid glitches. So what we can say is that we trade off the mechanical complexity of our earlier system for electrical complexity in the magnetic bearing system. What we think makes sense, what my research team is striving for is this kind of system on the right here, a bearingless motor system, where now you're using your motor to behave both as your bearings and your motor, and you're doing this all with a single set of drive electronics. And so because it's a single set of drive electronics, it's much easier to use any stored kinetic energy in the motor to keep your levitation going. You can kind of get rid of this need for battery backup system. So just broadly speaking, this is how we think it kind of makes sense in industry, and we'll talk more about the details of what's under this cover later in the talk. You could also use this for storing energy. So if you can spin your shaft up to high speeds very efficiently, well, you can store energy kinetically and use this for flywheel energy storage. And so we're also thinking about these kind of concepts. Okay, so why magnetic levitation, or better yet, when should somebody consider using magnetic levitation in a motor system? And my answer to this is when some of the following bullets are valued, when some combination of these bullets. So frictionless operation, contact-free rotors, an oil-free system, long rotational life, variable rotor dynamics, low vibration, and health monitoring. So, you know, put a different way, it's when you want your motor system to be smarter, right? When you want to be able to actuate it in bizarre ways, perhaps to change your rotor vibrations, to make it really, really quiet. When those lubricants cause you a very large pain point. These are when the value of magnetic levitation really shines, and the pain points that we talked about earlier are kind of minimized. So let's talk about some of those pain points. You know, I said that magnetic bearings are bigger. This is a bar chart, relatively scaled, comparing the force density that you can achieve with contact bearings, journal bearings, airfoil bearings, and magnetic bearings. And look, contact bearings, I mean, it's off the charts, right? Makes sense. You've got steel in contact with steel, 10 to the 5 psi. Oil journal bearings, you know, they're a lot lower. They tend to be bigger. And then magnetic bearings are down here at a piddly 100 to 200 psi. So this is pointing out the challenge we have in front of us. This definitely needs to be considered. What I like to tell people is that this kind of chart tells you that you're going to need to learn to use your newtons wisely. You don't want to waste them. And so we'll talk more about how this factors into systems later. The next thing that I want to introduce here is not about magnetic bearings as much as about electric motors. And so there's kind of this tendency to think, oh, well, if I've got this application, I want to drive it by a motor, that you can then go ahead and size the power rating of your motor independently from the speed that it's going to spin at. And in fact, that is not true. For any given speed that you want your motor to spin at, maximum design speed of the motor, there's going to be a maximum achievable power that you're going to be able to design that motor for. And so, when we're sitting down here at like 1,000 RPM, that maximum power is pretty dang high, right? And we're talking about gigawatts, so you're not worried about it there. But when we're talking about 10,000 RPM or 100,000 RPM or a million RPM, then suddenly these lines I'm showing up here, which are limit lines, start to factor in for what, it starts to inform you of what type of motor you should be designing and whether you can hit your spec or not. And so what are these limit lines? Well, they're characterizing different motor technologies. This is all data from a review paper from 2013 out of the UK. And so this pink line here is the limit line for interior permanent magnet motors. And so you can see that it has a lower speed power capability than surface-mounted permanent magnet motors. We kind of know this, right? If you put a carbon fiber retaining sleeve around magnets with a surface permanent magnet motor, you know you can achieve higher tip speeds, and therefore you're going to be able to get a higher power rating. Interestingly, solid rotor induction motors are actually rated the highest. Okay, so I just want you to kind of dwell on this. This is gonna come back up a couple times in the talk, but the reason for these limit lines is what we're going to play with next, and it comes about due to mechanical considerations of the motor. It comes about due to, well, you know, one thing I already gave you, which is the maximum surface speed of the rotor, or the strength of your rotor. At what point will it fly apart when you spin it up to really high speeds? How much surface speed can it handle before it breaks down? And so that's a mechanical design consideration. You design retaining sleeves for it. You can find some limits on this. But more relevant to us is the bending modes of the rotor, the length of the rotor. So it turns out that that most electric motors are designed to operate below the first bending modes, and the frequency that these bending modes occur at depend on the length of the rotor. So the longer your rotor is, the lower frequency that your bending mode will appear at, and that means that the lower maximum speed you can achieve. So if you're trying to scale the power of your motor, you basically have two fundamental handles. One is the radius of your rotor, and the other is the length of your rotor. You want to double the power of your motor? Well, easy, you can just double the length of the rotor. Except that if that causes a critical speed to come down within your operating speed range, you've got a problem. And so when we think about magnetic bearings and their low force density, that means that they are occupying more of our shaft length and limiting the amount of shaft length that's available for us to produce torque on. And so that's really the topic of this slide here, where if you think of kind of a classic motor system that's got magnetic bearings, you got your motor, you've got two radial magnetic bearings sandwiching it, you've got an axial bearing on one end. Well, all of these components are taking up a lot of length on your motor shaft. And that length that they take up, you know, if you figure, hey, I'm designing this motor for 30,000 RPM, you can kind of estimate, okay, here's the maximum length that I can have before my bending modes become an issue. Well, you can subtract from that the amount of length that these magnetic bearings are requiring, and that's the amount of length you have left to make torque upon. And so if these bearings take up a lot of length, you have less length to make torque with your motor, and therefore your achievable motor power rating becomes lower. And so that's what this plot is, you know, approximately trying to show you, that if you have magnetic bearings that are really bulky, you've got one power speed capability for motors that you design. Now, if you decrease the bulk of those bearings, you can shift this curve and make motors that are higher power. And so that's really one of the things that we've been targeting is ways to decrease that length. There's lots of research in this space, and it's one of the motivating factors for a bearingless motor. So if you take your classic motor with magnetic bearings, well, you can free up some space by merging your axial and your radial bearing into something called a combined radial axial magnetic bearing. And then you can free up even more space if you can just roll this last remaining radial bearing into your motor. And so we've got research on both the combined radial axial magnetic bearing and in the bearingless machines. Okay, so last big picture slide before we start rolling up our sleeves and getting our hands dirty on how these things work. Thinking about motor bearing technology kind of holistically, contact bearings, hydrodynamic bearings, mechanical bearings, they've been around for a long time. They're very mature. They can do wonderful things, but they've got all these pain points we talked about. How do magnetic bearings and bearingless motors fit into this? Well, magnetic bearings really came on the scene in the 80s. The very first rollout of this into a commercial product was in 1985. I've listed 1988 as a key date here. This is when the first International Symposium on Magnetic Bearings was held. This event still continues to this date. It just was in Rio de Janeiro this last summer, virtually though. And so magnetic bearings, they had kind of a slow growth for a while. It was limited by a lot of issues with control. Analog control works for magnetic bearings, but it doesn't work great because the tuning of magnetic bearings controller is really important for the stability of the system. And if you have uncertainty about your model, your plant, if it changes over time, it's hard to adapt to that with an analog control system. And so really a lot more action happened in magnetic bearings in the early 2000s when DSPs and FPGAs became more powerful and lower cost, and we were able to implement digital control and do cool things like auto tuning of our mag bearing system. And then now they've kind of flattened out again, and this is, in my view, largely because of the inherent limits of magnetic bearings in terms of force density, in terms of the cost of these systems. It's hard to get them down. It's hard to make them low cost. Their cost doesn't scale very well with power rating. Sensors always cost kind of the same thing no matter what power rating the motor is. And so if you place bearingless motors on here, well, bearingless motors are new, although I do date them back to 2001. And in fact, the concepts of bearingless motors also go back to the 1980s. 2001 was the first year that a company started in earnest to commercialize these. This company was Levitronics. They were formed in Zurich and ultimately developed a bearingless blood pump that became an artificial heart that was very successful, and some hygienic pumps for mixing devices in the semiconductor industry. So Levitronics has specialized kind of these niche markets where you really care about the levitation capabilities and you don't necessarily need a very high performance motor. And so I put a question mark out here because now we're at the stage where we know this technology works, but it's only been set up for kind of niche applications. And so the question is, what can it do as we go to, as we look forward in the future? What can we do with it? And I think it's going to go like this, but I'll let you form your own opinion from my slides here. Okay. So we talked big picture about this technology and its background and kind of set the stage. Let's now roll up our sleeves, write out some equations, and see how this stuff works. So I've got a series of slides for you here that we're going to step through. We're going to build up to how the basic radial magnetic bearing works, including its transfer function. And then we're going to pivot and talk about how bearingless motors work. And from there on out, we're going to chart out what the research trends are and what the promise is in this space to try to reach the lofty potentials I just summarized earlier. Okay, so magnetic bearings. I've got a simple system up here. This circle is meant to be an iron shaft. We've got a little C core up on top that we wrapped a coil around. We're going to put current in that coil. When we do that, we get a magnetic field that follows this blue line. And it's going to make this become an electromagnet, and it's going to cause that shaft to pull into it. And so we can write out expressions for the force using the Maxwell stress tensor. This is kind of a fundamental thing that we learned when we studied Maxwell's equations in our undergrad physics classes. Maybe you spent like 10 minutes on it, moved on. Well, it turns out that in magnetic bearings and bearingless motors, the Maxwell stress tensor is the fundamental tool that you have for analyzing your forces as produced by fields. So from the Maxwell stress tensor, we can calculate a pressure acting on the surface of our rotor that goes by the square of the field divided by 2 times the permeability of free space. So if we work with that expression, we can come out with an expression for the total force acting on our shaft as this right here in terms of our magnetic field. And we can, of course, figure out what our magnetic field is in terms of our current. And we get this expression down here where we can recognize that these first set of terms are all constants. They're all geometric constants. And so we can just call them the letter K. And we can see that the force in the y direction is equal to K, this constant K, times our current in that coil squared. Okay, so that's great. We've got an expression, but we've got a couple problems here. We're only able to produce forces in the positive y direction. We're not able to produce any force going down. And it's nonlinear, and we don't really like nonlinear systems. They're much harder to design controllers for. So what do? Well, we put a second core on the bottom of this shaft, and we excite it with its own current. And so great, now we have force is equal to this K times the difference of the square of the 2 currents. And that's great. Now we can produce force pulling the shaft down, but it's still not linear. And so we then break our currents out, and we say that, okay, we're going to flow a common mode component or a bias current in each coil, and then we're going to superimpose on top of it a differential current or a control current. And so if we say that each coil's current is composed of these two terms, plug these terms into this expression, we get out this expression down here for our force. So now we have force is equal to 2 times that constant times our common mode current, IB, times IY, which is that differential current. And so what we'll do here is we're going to hold IB constant. And if we do that, we can call this whole term up here a constant term that we'll label as Ki. And we can say that force is simply proportional to the differential current. Now it's linear, right? Ki bakes in the bias current. We're going to always flow the bias current, no matter what. But then we'll flow Iy, this differential component up here, in proportion to the amount of force that we require. And so this gets us to a linear control law that we like, because we can design controllers around that. All right, so that's how we make electromagnetic force on these. Now, what does this look like with power electronics? Okay, well, you can attach a single-phase inverter or an H bridge, a full bridge, to each of these cores, and then you can drive current in both directions. So that's nice. Whoa, there we go. Okay, so that's all well and good, but you know, it turns out that, and we kind of intuitively know that when we have our bias current flowing in these two cores, if we were to shift our shaft towards one of the cores, so for example upwards here, we'll get more field in this top air gap, and therefore it will start to pull into the top. And so our model doesn't yet include that, but I'm not going to get into it, but of course we can derive that dependency as well, and we'll define that as this constant K delta, which is an unstable stiffness. This K delta again depends on our bias current, but we take that unstable stiffness and we multiply it by the amount our shaft has deflected from the center of those two cores, and we get out an unstable pull force on our shaft. So our total force on our shaft is equal to that component that we control, we built up nicely, and then this component that I'm just summarizing for you, which is our unstable pull force. And this K delta term is going to be very important. This is what determines a lot about the stability of the system, and so we'll talk about that in a few slides. Okay, this is the complete picture of a magnetic bearing in the Y direction, and to create it in the X direction, we just take these cores and we just rotate them 90 degrees, and we do it again. And so that's how we build up a standard 8-pole magnetic bearing. So here's our cores in the Y direction. Now we rotated them 90 degrees, and we've got in the X direction, so we can produce X forces. For convenience, we can link it all with a single solid back iron, and we've got the classic 8-pole magnetic bearing. All right, and so again, like I was saying, this looks a lot like a motor. The steel is laminated. We've got a shaft, we've got a laminated target for the sensors as well, or for the shaft as well. And so that's the geometry. Let's now talk about control. So at the highest level, our control topology looks like this. And I'm going to start on the right side and then kind of bring you around the loop. So I've drawn our shaft here. And now I've just drawn a single of the actuators, but I mean that this is the full 8-pole bearing we just drew on the previous slide. I took off the other actuators so that I could draw a sensor in here. So I've got my shaft, I've got my actuators, and I'm going to sense the shaft's position. So I feed that shaft position back in to a feedback controller over here. So I've got a reference position, and a magnetic bearing, your reference position is always 0. You always want that shaft in the center of the air gap. I compare a reference to the measurement, I get an error in the shaft position. I can feed that into a position controller or a position regulator. Out comes a force command, and I can convert that force into a current that I want to flow in my bearing. And so this whole box here really is just a current regulator. So I take my force, I divide it by Ki, out comes my control current. I add in the bias current we talked about from a couple slides ago. Now I have the total current that should flow into this coil. I also have the current that should flow into the bottom coil that I'm not showing. I then feed that into a current controller, which commands voltage on power electronics, and voila, there we have our system. And the force law, again, for our system is summarized like this. And I'm now going to use this to derive the transfer function and show you the stability of it. So this is our force law we just wrote out from a previous slide. I'm going to club these two variables into a single variable that I'll call FCY for controllable force in the y direction, and I'll leave this alone. And so if I just write out the equation of motion, where mass times acceleration is equal to force, so force, I plug this in up here, I can write out the differential equation between y and force, and I get this plant right here, and voila, we have a right half plane pole. We have an unstable system. Not surprising, you intuitively know with a system like this that if you move your shaft closer to one of your magnets, it's going to want to pull in. It's like you've got an unstable equilibrium in the center when your shaft is equally spaced between your two electromagnets. And then if you pull it closer to one side than another, you'll get an unbalanced force that will pull it in. And so our job as a control designer then is to figure out how to stabilize this pole. Okay, so that's an overview of how magnetic bearings work. Just summarizing why you like them, why you don't like them. The key advantages, again, this contact-free operation can lead to very high efficiency and long lifetime. They're highly sensorized. These health monitoring opportunities. They've got tunable rotor dynamics. You can get rid of vibrations and very quiet operation. They're oil-free, but they're big. They require long axial length. Lots of power electronics and sensors make them expensive. Typically, you have to also integrate touchdown bearings so that if the shaft does drop, it drops on something that doesn't cause the motor to get damaged, and they can cross-couple with a motor. And so here is like a crude drawing of how you might try to put magnetic bearings on a turbocharger, and you can't do it because that turbocharger is spinning at such a high speed that the shaft length required by your magnetic bearings would just simply be would leave you no room to put a motor on it if you want to make an electric turbocharger. Okay, so that's magnetic bearings. Let's now talk about bearingless motors. Let's go bearingless. So again, a bearingless motor is a single machine that produces both torque and magnetic forces. It can replace one or more bearings, and you can think about this within the premise of a magnetic bearing, or the paradigm of a magnetic bearing, as that you're using the magnetizing field of the motor as if it was the bias field of the magnetic bearing. So the magnetic bearing required this bias field that your bias current created. In a bearingless motor, you're using the motor's magnetizing field as that bias field. It has a potential to solve a lot of the challenges of magnetic bearings, and that's going to become more evident as we go forward. But integrating things using the same hardware to produce torque and bearing forces reduces cost. It better utilizes space, more integrated, easier to fabricate. All these nice things. Okay, so let's take a little sidestep here and just talk through this example that I've labeled as being illustrative. This is an example from a textbook here, kind of the textbook on magnetic bearings by Chiba et al. And so our example is we've got this motor right here, and our motor has right now it's not flowing any current, so it's just got a permanent magnet rotor, and the field in the air gap of our motor is about 0.7 Tesla. This is a very typical air gap field of a motor without any current flowing, and I've given you some dimensions. I said the air gap diameter is 50 millimeters. It's got a rotor length of 50 millimeters. Okay, so it's kind of a small motor. We're going to assume that the mass density of all materials is 7.65 grams per centimeter cubed. This is the typical mass density of steel and magnets. And so the first thing we're going to do is we're going to go use the Maxwell stress tensor like we talked about earlier and calculate the force that's acting on the stator teeth over the magnets. And so we can see that if we do that with this 0.7 Tesla going up here, 0.7 Tesla coming in here, we get 255 newtons acting on the top and bottom stator teeth. Now, I mean, there's no net force in the rotor because they're acting in equal and opposite directions, but yet there's force there, right? Just because of the presence of that magnetic field. Now we can compare that to the mass of the rotor from these dimensions. And we can see that the rotor weight is 7.3 newtons, which means that the teeth of this motor are already supporting 35 times the weight of the rotor, but yet not creating any net force on the rotor. They're not actually doing anything useful for us, but they're already bearing the load of 35 times the rotor weight. All right, so the next calculation we're going to make is we're going to modify the air gap field in the top and bottom so that we now have a difference in force between the top and bottom tooth so that it supports the rotor. And it turns out that all we have to do is add 5 milliteslas to the top air gap, take 5 milliteslas off the bottom air gap, and suddenly we are supporting the rotor's weight. And so I like this example because it shows the immense untapped capability of electric machines to produce forces. You know, I mean, I think it's quite striking that without flowing any current, just this kind of standard small electric motor is already producing force on its stator teeth that is 35 times the weight of the rotor. And that then by only having to modify the air gap field by 5 millitesla, we're able to then suddenly get a useful force out that can support the rotor's weight. So that's what bearingless motors are about. It's about trying to tap into that unused force potential of electric machines. It turns out that the way that you make these forces, the only way, in fact, to make force on your rotor is to have air gap fields that have different number of pole pairs such that one so say that your magnetizing field has 4 pole pairs, you need to add another field that is plus or minus 1 pole pair. So you'd have to add, if you have a 4-pole motor, you'd add a 2-pole or a 6-pole air gap field to make it make forces. If you had a 4-pole, I'm sorry, if you had an 8-pole motor, you'd add a 6-pole or a 10-pole field to make forces. And if you, it's well known already that if you add a field that has the same number of poles as your rotor, you make torque. But the idea in a bearingless motor is that you add another field that has a different number of pole pairs by plus or minus 1, and that's what that makes forces. So in this machine right here, we've got a 4-pole rotor, right? North pole, south pole, north pole, south pole, 4 poles, or 2 pole pairs, and we're going to add a field on top of this, which is a 2-pole field. So we've got a 4-pole rotor, we're adding a 2-pole field, and that is enhancing our field on the right side of our air gap, weakening it on the left side. And so we can see if we were to use that Maxwell stress tensor and we're integrating B squared, we're going to have a net force going in the right direction. So bearingless motor, usually we'll use a multi-phase winding. And so, you know, if we've got a phase U that creates a force along the horizontal axis, maybe phase V will create 120 degrees off, phase W would create it 120 degrees further rotated. And so now we've got 3 phases that are each able to make a force vector all 120 degrees rotated from each other. You can create a net force on your rotor that is at then any arbitrary angle, a net radial force at any arbitrary angle. So that's kind of how the electric machine fields work to create force. Let's now talk about how the drive electronics work. And so normally in a motor, in a bearingless motor, or traditionally, you'll do this with 2 sets of windings. One winding is your normal, regular old motor winding. And so you attach that to a motor inverter, you control it as you always would. Maybe that's DQ control, maybe it's V by F, maybe it's just a power grid. Nothing new there. The second winding is what creates that plus or minus 1 pole pair field, is what creates that suspension field. And that you attach to a suspension inverter to regulate currents to create that field. And the force model for the bearingless motor can be written out to look a lot like a magnetic bearing. Only now it is complex. So your force vector in the X and Y direction can be set equal to a complex constant times the space vector of your suspension terminal currents plus the unstable displacement stiffness again times any displacement. So this looks just like the control law we wrote out for magnetic bearings, only now it factors in both the X and the Y direction. And this complex constant here, it turns out it has an angle that will rotate along with your rotor's rotation. All right, now we'll ease up on the math for a little bit. We'll give you a complicated diagram. So how do you control these things? Well, if this is our bearingless motor, up here is our normal motor control algorithm. So I've just drawn this out as field-oriented control. We've got a D and Q current, but the point is that this is this regular old motor controller. Everything we add down here is new for magnetic levitation. So like the magnetic bearing, you're going to feed back in X and Y position. You're going to use that to create an X and Y force command. And then you need to know more information about your system. You need to know that Ki magnitude and angle in order to figure out what currents you should be flowing. And then you use a current regulator to obtain those currents in your machine. All right, so that's the theory. Now, what's kind of the current state? What can you do with this kind of thing? Where's it going? Well, this technology is really gaining a lot of attention recently. It's really growing in attention, I should say. And so my group did a review paper on this a couple years ago, and we've been updating it ever since. And so this is a count of all the publications on bearingless motors that have experimental results. And you can see that we've got about quadratic growth. So on that y-axis is the total number of papers within a given period of time. Each of the colors represents the type of motor technology. So this salmon color is all the bearingless motor papers with experimental results over that period of time. And then each of these color bands are different types of bearingless motors: permanent magnet motors, bearingless reluctance motors, bearingless homopolar, bearingless induction motors. And so you can see that we've got quadratic growth, and really bearingless permanent magnet motors have been a pretty dominant mainstay here. But the point I want you to make here too is that yes, this is really growing and attracting a lot of attention. Something must be going on here. What can you do with this? Well, there are lots of different concepts for what you can do with your ability to actuate radial forces or normal forces, and how this could apply to thermal machinery. Everything from having two twin bearingless motors on a shaft that span an axial magnetic bearing, to having a combined radial axial magnetic bearing to support some of the degrees of freedom and a bearingless motor elsewhere, to more exotic configurations that like a cone-shaped air gap that can allow your bearingless motor to produce axial as well as radial forces. This is a lower technology readiness level. It's very hard to make a cone-shaped air gap motor. To what are called bearingless slice motors. These are really neat machines where if you have a very large rotor diameter relative to axial length, the machine is able to use passive forces to keep itself supported axially in the tilting direction. All you have to do is control radial forces to keep it centered. So these are lower cost, lower power. And also you can use this technology to supplement conventional bearings. So if you have a motor system that's got rotordynamic issues, got vibration problems, you can use a bearingless motor to tweet out corrective forces and dampen those vibrations. So these are different concepts. But how does the performance stack up? And right now, I'm sad to say the performance is lacking. If you remember back to when I showed you that speed power plot quite a while ago, I've just reproduced it here. And these are all, all these data points were for motors with bearings. Now I'm going to show you a plot next to it that is for motors that are bearingless. And you can see it doesn't compare so well. All these data points are example publications, or all the publications that we have been able to find of bearingless motor test results. And you can see that these machines are simply not obtaining the same speed power capability as motors with bearings. And we'll drill down this a little further. We can pick out individual designs on here that are getting most interesting, and we can see that the earliest one was from 2000 from this company in Zurich called Sulzer. They built a 30 kilowatt, 3000 RPM induction machine. Very good. 2011, this was bested by a 40 kilowatt permanent magnet machine, but not with really great efficiency, right? Not quite what we would expect from a permanent magnet machine. It's kind of concerning. Very recently, Tokyo Tech published a 62 kilowatt machine. Better efficiency, pretty high speed. But still, when we talk about permanent magnet machines around 30,000 RPM, we're usually thinking about 97% efficiency, 96, 97, maybe 98%. And so there's room to grow here. If we just take all the bearingless motor test results so far, we plot them on a curve with IE4 efficiency, you can see that we're frequently below the IE4 efficiency numbers. So why is this? And I'm going to step you through some reasons for this and some solutions that we and others are working on. And the bottom line is that we can do better and we will do better. In my opinion, a large reason for this underperformance is that in the early days of this technology, the focus was very much on applications that didn't care about efficiency. It was like these blood pump or hygienic devices where you really cared about having the magnetic levitation and having a certain form factor for your rotor, and what they were doing to the blood cells or weren't doing to the blood cells, but you weren't trying to push meaningful amounts of power where you were very concerned about efficiency and torque density. All right, so so my group's focus area and really where I see a lot of the research going on in bearingless motors across the world is really targeting these three things: reducing cost, increasing motor performance, and more precise and robust control of the machines. And so I'm going to present you some results now and some endeavors, some directions rather than results in each of these areas. And so we've been thinking about this a lot for 30,000 RPM, 50 kilowatt machines, and we've gotten paper studies, not hardware results, but paper studies, where we're able to show bearingless surface PM machines up in the 97-98% modeled efficiency. So again, this isn't validated. Only believe it, you know, take it with a pinch of salt. And induction machines that are over 96% efficient as well. So we've been working now on building up prototypes and getting results. These are pictures of my students building things in the lab. So yeah, I'm going to present you a few directions, research trends in each of the aligned with each of these bullets. So the first reason that I think bearingless motors have not been doing as well is this tendency to make them by introducing a second winding to the machine. And the second winding is bad news. You know, one of the most important design handles you have on your machine is how many conductors you can pack into a slot. And so if you, for making torque, and so if you're giving up conductors in your slot to then be able to create suspension forces, it doesn't bode well. And it turns out that because you have to design these machines for a worst case scenario, because you have to design them for a corner condition and forces, you end up allocating about half the slot space to the levitation winding, but then only using a couple % of it under normal operating conditions. So you really hamper your ability to make torque. And this decreases power density, it decreases efficiency. It's also hard to manufacture motors with 2 windings in the stator slots. And so one of the things that's been going on in the community, not just from us, but really internationally, has been developing stator windings that can use the same coils for making both the force fields and the torque fields, both suspension fields and the torque fields. And so this is kind of, you know, at first pass, a magical thing that you're able to use a single set of coils to create 2 different air gap fields, one with P pole pairs and then one with your suspension pole pair fields, right? Seems impossible. But nonetheless, it is possible. A little hard to show it, but with multi-phase windings, you can indeed deliberately produce multiple harmonics in your air gap, and this is often done. My group is focused in on these 2 types of windings over here, where you have multiple inverters. So maybe this is the easiest one to understand here. You got a motor inverter and a suspension inverter. If you look at the current paths, you can see that in some coils, the current flows in the same direction, and in other coils, it flows in opposite direction. And by playing games with the direction of the current in each of the coils, you can have these 2 inverters produce different number of pole pairs of field. And it's been shown in numerous studies that doing this has tremendous improvements in the performance of the motor. You're suddenly able to get designs that have high power density compared to designs with the separated windings. These designs can reduce copper losses by upwards of 39%. So it's a big deal for the performance capabilities of the machine. But the power electronics, when you go to this kind of winding approach, get a little bit more complicated and expensive. And so we've been, as well as others, have been working on ways to reduce the power electronics expense. Here, this is a study that we did where we replaced, we have our suspension inverter operate off of a floating capacitor that we actively rectify a voltage on as energy is drawn through the motor coils. We're also working on concepts that are reducing the amount of components in drives when you have kind of a twin bearingless motor arrangement. The other reason that these things aren't performing very well is that bearingless design is hard. The design space is much more restricted. You know, if you think about what you care about in a normal motor, it's, you know, torque and power density, torque ripple, efficiency. Well, for a bearingless motor, you have to add in there the ability to make force. You know, how many newtons per amp of current you're creating, and you worry about force ripple. So in a regular motor, you worry about torque ripple. Here you have to worry about force ripple. We call it force vector error because force ripple occurs in both the x and y directions, so it's really more of a vector error. But this has implications for your stability. So your design space is restricted. You have it's harder to get high performance designs. And in some cases, fundamental aspects about your motor just don't work very well when you make it a bearingless motor. So for example, a squirrel cage induction motor really struggles. If you add a suspension field to the air gap of a squirrel cage motor, that suspension field will appear at a different slip relative to the rotor than your magnetizing field does. And so it will induce its own set of currents in the rotor that will attenuate force, it will create torque, they do all kinds of nasty things. So there's been an effort from us as well as from others to develop specific rotors or special rotors that don't induce currents from the suspension forces. And so we've got an example here on this slide. This is actually a paper under review right now that we were able to get a 91% reduction in the amount of current linking the current inducing the rotor due to suspension fields. Okay, so
sorry, Eric, sorry to interrupt, but
yeah, no problem.
Already past 1 hour, and I think it's better to wrap up and give people a chance to ask questions.
Sure. Do you mind if I just take another minute to?
Of course, yeah. But talking about that, there's actually we do have one question for you.
Oh, sure. Go ahead.
Yeah. Matt,
can you improve the performance of an existing bearing motor design by reducing the forces on the bearings?
Yes, you can. Yeah. Yeah, so I think that kind of the classic example of that is trying to get rid of vibrations from the system. And one of the reasons that let's see here, I'll pull the slide back up, that I like this concept a lot is that if this is kind of like an intermittent issue that you have, like as in the forces on the bearings occur at some operating points but not at other operating points, these advanced windings that use the same coils for levitation forces and torque get you a lot of, they give you a lot more degrees of freedom to play with, because you can have your regular old motor performance, torque capability when you don't need your levitation force capability, but then in those instants of time, or when you're passing a critical speed, or you've got a compressor surge event or something that's loading your bearings, then all of a sudden your motor drive can ramp up and make forces that help your bearings out.
We do have another question from Scott.
Well, I'll let you finish, and then I have a couple questions, but I'll let you finish.
Oh, okay. Thank you.
Sure. Okay. I promise I'll wrap up here in just a minute. So we've been doing optimization. We've also so we've been doing careful optimization to try to eke out as much performance as we can, and this has been quite successful for us in getting higher efficiencies. And we've also been working on some advanced control techniques to make sure that we're always actuating force in the direction that we intend to be, to reduce that force vector error with control. And we've also had some nice success here. And then we've been working on a technology called 3-pole bearings, or 3-phase bearings, that are radial bearings that can be operated with a 3-phase motor drive instead of all those single-phase inverters. So pulling it all together, we're getting machines that have this much higher efficiency and torque density, and are really indistinguishable in performance as compared to the highest performance motors that use contact bearings. Again, this is optimization and paper modeling results, and we're now pushing forward on experimental validation of these ideas. So finally, yeah, again, to summarize, bearings are the weakest link in motor technology from our point of view, and whether magnetic levitation makes sense, though, really depends on the application and how you value the benefits that can come from magnetic suspension, and where the weaknesses or the challenges, how much they hurt you. So, you know, if reliability, lifetime is really important, or getting rid of lubricants is really important, then magnetic levitation has a lot of value. But there's a lot of room for improvement in terms of force density, cost, and integratability. All right. Well, thank you. I promise I'm done. Last slide.
Great. Thank you, Eric, for this really nice tutorial on bearingless motor. Let's thank Eric for this nice talk.
Yeah, you're welcome. Yeah, what questions can I answer?
So I have a question. So you showed on one of your earlier slides that you have sort of one suspension circuit and one sort of normal circuit. I don't remember what you call it. But I mean, if this motor is in R3 and it has some length, don't you need at least two suspension circuits? Because, I mean, there's at least two modes that are unstable, right?
Yeah. So let me pull up this slide here. So, I mean, in general, a shaft has 6 degrees of freedom. So, you know, I mean, like if you can see my pencil, you got to support it radially, you got to support tilting, you got axial, and you got torque. And so, in general, you have to figure out a way to support all 6 degrees of freedom. Now, sometimes you can use passive forces for some of those degrees of freedom, and that's what's going on here. Other cases, you know, you're going to have to figure out a way to actively actuate it, whether that's twin bearingless motors or an axial bearing. I don't know if I'm quite getting at your question.
Yeah, I think you need at least two on that one on the left, right? You need one. You need a bearing on either end, right?
Yeah. So on the left here, that's why it's drawn as 2 bearingless motors, so you get the radial forces on both ends. Yeah. Now the interesting thing is this one over here, which because it looks like kind of a hockey puck or a pancake shape, is able to use passive forces. So you only need to actively actuate in one plane.
Yeah, I've seen that. Yeah. So my other question is, you know, you referred to these as frictionless, but in fact, there's eddy currents that are generated in the shaft, right? So doesn't that cause friction as it rotates, and how does that compare to a mechanical bearing?
Yeah. That's a good point. Yes, absolutely. There's not only eddy current losses, but there's actually iron hysteresis losses, right? So the nice thing is it compares well, is the short answer. For magnetic bearings, typically if you do a side-by-side comparison study of like any bearing technology with a magnetic bearing, you pretty much, this is kind of a cop-out answer, you always find the magnetic bearing has less losses. So for example, there's lots of case studies right now for wastewater aeration equipment and using magnetic bearings in place of oiled journal bearings. And usually you find that the oiled journal bearings, because of the large axial loads, may have upwards of about, I don't know, 2 to 5% of the motor's power rating is appearing as losses in those journal bearings. And the magnetic bearings typically are around 0.1 to 0.2% of the motor's power rating and losses. So it's quite a sizable reduction. Now, in some applications, the losses in your mechanical bearings aren't so great. I mean, that's kind of, these compressor applications are really where you see the large losses when there's large forces that are being supported. But if you're just supporting gravity, then you're maybe not making much of an efficiency argument when it goes to magnetic bearings as compared to contact bearings. Now, the second part of your question, let me answer it in terms of bearingless motors. In a bearingless motor, eddy current losses, iron losses, you are not necessarily adding any significant new loss than is already present in your motor. So if you have a permanent magnet motor and that rotor is spinning, it already is causing eddy current and iron losses in the stator. And we find that just to support the shaft weight of the rotor, you don't have to change your magnetic field very much at all. You know, it's like, you know, that 5 millitesla example I gave, right? And so they're really, at least in our FEA simulations, it's like within the accuracy of our FEA tool for us to be able to see an increase in losses there on a well-optimized, carefully done design. And so it doesn't really add any sizable increase.
Right. Thanks, Eric. Any other questions from the audience? Actually, I do have a couple. So one is that, you know, in conventional mechanical bearings, you know, they often suffer problems like unbalance and eccentricity, right? So for magnetic levitated motors, how do you make sure that, you know, the rotor dynamics, you know, there's no, you know, how do you avoid these eccentricity issues?
Yeah. So that's kind of the fun thing with magnetic levitation is either a magnetic bearing or a bearingless motor. It's how well of a job you do as a controls designer. So it's totally in your hand. We sort of talk about these concepts of dynamic stiffness and what your bearing stiffness appears at each frequency or each rotational speed. And that's all having to do with how you placed your closed loop poles of your system, or how you picked your, you know, if you're doing PID controller, how'd you pick your KP, KI, KD? And so there's lots of fun stuff you can do with, like, between gain scheduling. You can make your controller gains change as a function of rotational speed to actually move around critical bending modes or critical modes of your shaft. One of the interesting things about magnetic levitation is that it opens up the possibility of letting your shaft intentionally have some orbit or some run out, some eccentricity. And sometimes we do this, especially in compressors, where it's maybe not so critical that your shaft be precisely centered. Like, you know, there's some clearances with the centrifugal compressor, but maybe it's okay if you have 100 microns of run out. So what we do in those cases is we say, hey, you know, we'll take the 100 microns of run out over the watts of loss that would be caused by us flowing current to fight rotor unbalance forces. And so then we'll actually put like a notch filter in the feedback path from our sensors, so we restrict the controller from reacting to unbalanced pull forces. And yeah, is that answering your question?
Yeah, so a lot lies in the control of this type of machines, right?
Yeah, it's purely a control problem. And so that's a good thing and a bad thing, right? Like, how much you trust your embedded systems engineer.
Oh, I do have another question from Matt.
Yeah, I'm just wondering, so are these things viable at higher RPMs? And if so, what would it take for them to be competitive with air bearings?
Yeah, great question. Yeah, so they are viable at higher RPM. In fact, a fun company to look at for examples of this is Rotor, also in Zurich. Zurich is the city of Zurich comes up a lot in magnetic levitation because of ETH. Rotor is making 1 million RPM motors for I think reaction wheels in aerospace, optical. Sensing kind of applications where they're spinning a mirror really fast, and things like this, right? And so anyway, this technology does work at really high speeds. In fact, it's liked at these speeds because of all the contact-free aspects of it. Now, compared to air bearings, that's a great question, and always application dependent. So, for example, in the wastewater aeration equipment space of all things, air bearings and magnetic bearings are kind of duking it out right now. There are companies that will sell wastewater aeration equipment that's spinning at like 30,000 RPM and is air bearing supported, and there are companies that will sell you the same equipment and magnetic bearing supported. The trade-offs and the differences are basically the ability to actively control the magnetic bearings, so that the air bearings present a very nice solution but they have a few limitations. One is that there's a minimum speed before they'll pick the shaft up. So every time you start and stop that motor, it's got to sit back down and rub on the surfaces of the journal. The air bearing companies will tell you that's no problem. They've got their Turbology figured out, and they can support this many times. Some people will say that there is a problem there. I don't know. The magnetic bearing, it can levitate at 0 speed, so it can pick its shaft up at 0 speed, and then it can support it the whole speed range. Also, the magnetic bearing allows you this handle of controllability that you can change and tune your dynamic stiffness on the run without it being just a fixed design time issue. The drawbacks, of course, magnetic bearings, there's lots of sensors, lots of electronics. They have more capital costs as compared to air bearings. And then the other thing that's of note is, air bearings don't work in applications where you don't have air, right? So if you're in a vacuum environment, the air bearing isn't going to go. HVAC chiller compressors is a harder story as well.
Interesting answer. Okay, thanks.
All right. Thank you, Eric. And any other questions?
I'll add one thing to that. One of the intriguing ideas that could be pursued with this has been done a bit with magnetic bearings already, but I think that there's an opportunity with mag bearings and air bearings. Air bearings have a stability issues when they get, maybe I shouldn't say it like that. There's a speed range that they work at, and if you try to exceed that speed range, what the limiting factor is that they become unstable. There's a phase delay between the force that ends up appearing on the shaft in reaction to displacement and the displacement. And so one of the interesting ideas here is to use mag bearings to try to correct that disturbance. And so by having a combination of a mag bearing and a foil bearing or an air bearing, you could get to higher speeds. Now, this idea wasn't so interesting for magnetic bearings because they're so big and so expensive and everything. But if you're using air bearings on a motor, for example, it suddenly becomes more interesting to make that motor a bearingless motor and to try to correct that force, because you're not adding new hardware or minimal new hardware.
Might be good for optical lathes.
Ah, yeah.
Yeah, great. So I see no more raised hands. I guess we can wrap up this talk, and let's thank Eric one more time.